Hi, it's Juan here. Did you know that TornadoVM can run faster than OpenCL Native for some applications? Is that even possible? If so, how? Well, short answer, yes, but also no. Let me explain. So on one side, TornadoVM is more than a translator from Java bytecode to OpenCL or Java bytecode to CUDA. It also has an optimizing JIT compiler and optimizing runtime, so it applies compiler optimizations and runtime optimizations. So it could be possible. On the other side, well, if the baseline application, if the native application has not been optimized, then it's not a fair comparison. In this video, we will explore this topic in detail. So this is what I'm gonna do. We're gonna start analyze this topic in the context of one application, matrix multiplication. This application is widely used these days for AI and deep learning, so we're gonna choose this one. And we're gonna analyze performance starting from the Java side. So we're gonna start with Java application, and then we're gonna optimize the Java application to run as fast as we can. Then we're gonna start with Tornado. We're gonna deploy the application in Tornado to run on an NVIDIA RTX 4090. This is a good one. And then we're gonna compare the performance we get from Tornado against OpenCL Native. And we will see there some performance differences. So for the second part of the video, what we are gonna do is to analyze what TornadoVM applies under the hood and take those optimizations and manually insert them in our OpenCL C++ program in order to match the performance that we get from the Tornado side. This is gonna be a fun one, so let's do it.
Let's start with a baseline implementation. In our case, we're gonna select the Java sequential matrix multiply as a baseline. One of the main reasons is that TornadoVM, the way it's implemented when you want to use TornadoVM is that takes as an input, right? You start with the Java sequential implementation and Tornado will parallelize that application. However, we will change baselines later on in this video to make it harder. But let's start with something, and that something is the sequential implementation for now. So if you take a look at the code, by the way, the whole code is available on GitHub. I'm gonna put in a link in the description down below. And you can take a look, and you can modify, you can run, you can try to reproduce the numbers and so on. So this is the matrix multiply. This is the canonical algorithm. And we see that we have three parameters, A, B, and C, of type float matrix. This float matrix is a custom type also defined in this class. And it contains the dimensions mn, so this is the matrix size. Okay, and the only special thing about this is that it's using the Java memory, the Panama for an API, okay, to allocate off-heap memory. We see a segment declaration here, and the set and get, we use that segment to access the data and to get the data. And there are a few utility methods, for example, init random, just to initialize the matrix. Okay, so we're gonna run this on a server, right? But because we're gonna analyze the performance of these different applications, we should discuss the machine in which we're going to run on. And I have here a table just to discuss quickly. So we're going to use a server with an Intel processor i9-13900K. This machine has 64 gigabytes of RAM, and this machine also has an RTX, an NVIDIA GPU RTX 4090. We're going to use this later with Tornado and also with OpenCL C++. So this machine has the OS installed is Ubuntu 22.04, and we're going to use the TornadoVM 109 dev. It's quite close to finalized, so it should be quite close to the official 109 version. And the JDK we're going to use is JDK 21, and you can see the version here. A few more details about the application. So we're going to run the canonical matrix multiply. We discussed this already. And we're going to fix the size to 124 by 124. So you can run, obviously, any size. If you run very small sizes, you're not going to see any benefit by running on GPUs, right? Because GPUs is a throughput machine. You need big data and heavy compute to get some benefits. However, this size is also very small for GPUs, or a bit small for GPUs. But if we increase the size, the Java part will take a lot of time, and will take a lot of time to evaluate. So this is a kind of a compromise size. 124 by 124 is a reasonable size, and we can see performance very clearly. Another thing I want to mention is we're going to use FP32 values. It's a float value in Java. Obviously, if you run on GPUs with less precision, let's say FP16 or even FP8, you're going to see also massive speedups as well. However, for this experiment, we're going to stay with FP32 values, also for the native part, or OpenCL C++ part, and Tornado side. Again, all the examples can be found on these two repos. I put it on GitHub. The first URL corresponds to the Java and Tornado examples. The second one corresponds to the OpenCL C++ that we will take a look later in great detail. Okay, so with that out of the way, let's run it. I have the environment prepared here. Okay, this is the server, and here is the actual repo that I was talking about for running the example. So we're going to start with the Java sequential implementation. Let's turn this off. Okay, we will discuss this later with Tornado. And let's start with the Java. So what we want to do is to run only the Java sequential version. So we pass this flag to our implementation. So if we run it, it will take a while. And what we do is to run several times the same method. I think it's around 10. I think I put it 10, but you can tune this number if you want to. And you can see that the first time takes around 2.2 seconds, then goes down to 2.1, hopefully a little less every time, because we get the JIT compiler and so on. So a few words about performance analysis here. We are running with a small number of iterations just to show performance, right? Initial performance numbers. However, these numbers are quite close to that actual performance you're gonna get. How to get the actual numbers? Well, you might want to increase the number of iterations, let's say to 100 iterations or 1,000 iterations, depending on your application, or you can use a specialized framework like JMH. I have a tab over here with JMH already done, if you like, and we will. I will show you the numbers at the end, okay, at the very end. But just keep in mind that. So I must say that these numbers are actually very, very close to JMH framework because this kernel is heavy compute. All right, so the sequential implementation for the 1024 elements by 1024 takes 2.2 seconds to run on this machine. This doesn't tell us anything unless we compare with something else. Let's try to make the Java version faster. So let's go back to our code. I'm going to discuss how we can we can make this faster. One easy way is to parallelize the application. For example, by using Java streams. I have a version here that implements this application by using Java streams in the two outermost loops. So for these two loops, okay, and we will see the performance in a bit. Another strategy, instead of using Java streams, could be by using explicitly Java threads, okay? And this is the code to implement Java threads. I'm not gonna talk about the details. I'm gonna pass quickly because I want to analyze in more detail the Tornado code and the GPU code. Okay, so one thing I want to mention is that the parallel streams, okay, this one, we will see later that it performs a bit faster than Java threads. But the reason we will discuss later is that we are using two levels of parallel streams, one for the outermost loop, another for the innermost loop. So we have more parallel threads running in our system, if you like, while this one only parallelizes the outermost loop. However, the differences are not that big. let's say. Because at the end of the day, if you have 32 cores, like is this machine, you only have 32 streams in parallel, right? You might have more threads concurrently, but in parallel you have 32 streams. Right, so another strategy is to combine this with the Java Vector API. So I have two versions here. One is the sequential implementation using Java Vector API, and the other one is parallel streams in 2 dimensions using the Java Vector API. One thing I want to mention, to use the Java Vector API, you need to transpose the second matrix. This is because otherwise you don't get correct results. So the application is correct, it's syntactically correct, but semantically it's not correct. So you need to transpose this. And that has an influence in performance because elements of being laid out in consecutive memory, okay? That's an optimization we're applying here, and therefore we can see a bit of extra performance, not just by using the Vector API, also because the matrix B is transposed. Okay, so we have all these versions. Let's run it and see what we get. So I have another flag called only Java, and it will run all these Java versions, starting with the Java sequential again, and then we'll run the streams, the parallel streams, the multi-threaded, the sequential with the Vector API, and the streams with the Java Vector API. And let's see what we get. So as you can see, it's around 2 seconds, 2.1, 2 seconds to run the sequential implementation. Okay, and I will switch to the streams one. So we can see that it's way faster. It's around 93 milliseconds instead of 2000 milliseconds. Then for the Java, so the threads, okay, the thread implementation is around 97 milliseconds. This is, you see, the difference I was talking before. This is slightly faster just because we have more threads running. And then the vectorized version. So the sequential vectorized is around 190 milliseconds to run compared to 2000 milliseconds that was before in the sequential implementation. And the one we are interested is this one, which is the fastest one. This is the parallel streams using the Java Vector API. And we can see that in this machine, for this configuration, for this matrix size, it takes 14 milliseconds to run. I must say that this is quite impressive, okay? We're using the whole machine here. So this machine has 8 cores that can be used as a hyperthreading cores and contains the AVX and AVX2 instructions. This architecture is a bit different because it's a hybrid architecture. Contains what is called P cores, performance cores. There are 8 of those. With hyperthreading, you get 16. And then you have 16 of E cores or energy efficiency cores that you can use also for compute, but the frequencies are different. But it seems like we're using quite a lot of the machine to run this application, which is quite good. And I'm pretty sure you can still optimize this version, but we're going to stay with this as the fastest implementation in the Java side. By the way, if you want to compute the actual performance, what we get until now is, well, let's take this number. Let's try to compute quickly. Our calculator. It's an amazing calculator that we have here. And then let's take the fastest. It seems to be this one. No, sorry. This is in the number of nanoseconds, so we should get this number over here. So we can see that it's around 150 times faster, this version. It's quite good, it's quite impressive. Again, when you use JMH, you will see this. It's even a bit faster. I think it's around 155 times faster. Okay, with that out of the way, let's talk about Tornado. So let's jump to our implementation and let's discuss quickly the TornadoVM implementation. And here is the main method we want to offload for the GPU in Tornado. This is the Java sequential. If I remove the add parallel, okay, this is the Java sequential implementation. And there are these parameters, A, B, and C, and the type is a bit different though. The type is matrix2D float. It's a Tornado type. This is because Tornado doesn't offload any custom type, has its own types, set of types, okay? But it's very similar to the float array I showed you before, okay? So we need to transform this upfront. But the algorithm is the Java sequential implementation. So this is the method we want to float, and in Tornado we need to do something else as well. We need to specify that we want to float exactly this method. So let's go back to the add parallel. And this is done in this method, create TornadoVM plan. So we create a task graph, okay? We identify that the method to float is the one specified here. This is actually a lambda expression. This is syntactic sugar for a lambda expression. Okay, it's this one. These are the parameters for our method. And then we create an execution plan from this task graph. We warm up first and we select the first device that we have available. And then we return the execution plan. And this is done down here. We transfer the data. We create the variable for storing the results. We have the execution plan, and then we call execute, as simple as that. So how fast or how slow is this version? Let's jump in. So if I run with the flag, I think it's called, I think it's, I don't pass any flag. I have the scripts over here if you want to take a look. Let me take a look because I can't remember now. There we go. So to run all versions, you just don't use any flag afterwards. So if you run that, it will run all the versions again. Okay. You can select only Tornado, but let's start with let's run everything and analyze quickly. Again, this is around 2 seconds. In JMH is 2.1. There might be some thermal throttling in that, but this around 2 seconds. So again, the fastest Java was around 14 milliseconds, and Tornado is down to less than a millisecond. Okay, it's less than a millisecond. So this means a speed up more than 2000x performance, right? Okay, because 2000 milliseconds is less than 1 millisecond is more than 2000x performance. Okay, that's great. Okay, but how close or how far is Tornado compared to, let's say, a native GPU program to run the matrix multiply on the same hardware, on the same configuration? So to do that, I provide an example. Let's jump to C++ now. This code is also available on GitHub. I will put a link in the description below. And essentially, we have here multiple kernels. We're going to run this one, this matrix multiply. This is how you express matrix multiply in OpenCL. We're going to run OpenCL. So you get the 2 thread IDs, these to run in parallel, and then the final reduction here, which this is the work to be done per thread. Okay. So if we run this version, okay, I'll recompile that and run it. First of all, the GPU used is not the right one. It's using the Intel HD graphics. We want the RTX. We can stop it. And this is a parameter for this script, for this program, called -platform -p, and then you pass the platform name. I can tell in this server, the GPU platform, the NVIDIA RTX is the platform 2 for OpenCL. Let's pipe this. Let's see if we get the 4090. There we go. Okay, so we got the execution for the 4090 GPU, and it's running matrix multiply, the same size, okay, on this machine. And if we scroll down, this application runs for 100 iterations, and then at the end we get a report. The kernel time, this is just the execution of the kernel, the copy in time, copy out time, and the total time. We're interested in the total time, which is equivalent in Tornado when we compute the total time, just to be more fair. Talking about fairness, let's mention something else. You see here that the writing time is 0. That's strange, okay? If I run again, the first time is not 0, we see a number here. This is because I already prepared the C++ code to cache input data. Because Tornado also, by default, caches input data. If it's declared as read-only, it will cache data the second time you run. Okay. So if we want to compare apples with apples as fair as possible, we need to also to cache that. So just to keep in mind, this work is already done. So let's run it again and see the total time. We see that Tornado is 4.7 milliseconds. Sorry. So OpenCL C++ is 4.7 milliseconds, while Tornado was less than a millisecond. That's impressive. This is around 5 times faster for TornadoVM compared to OpenCL C++. Now, is this possible? Well, as I mentioned at the very beginning, yes and no. Yes, well, we're seeing this is possible, but why? This is because Tornado is more than just a translator. It also optimizes the code. Okay, we will see in a bit all the optimizations are enabled in Tornado automatically for us. It's quite impressive. But the reason is that we are comparing with a version, an OpenCL version that hasn't been optimized. So we should optimize that version. And the reason I'm saying no is this one, because the code hasn't been optimized, so it's not fair. But on the other hand, the input application that we choose was the matrix multiply in Java expressed in sequential. In Java, when we wrote the Tornado version, let's go back to the Tornado program. Over here, let's go to the create, where is it? Create execution plan. There we go. This version doesn't have any optimizations in it. I mean, you can think about this add parallels optimization. It's a hint for the compiler, it doesn't optimize. But anyway, apart from that, there is not any other optimization. And these two are equivalent to the thread ID in OpenCL when we get the thread ID for each dimension. Dimension 0, dimension 1 in OpenCL. I'm not going to explain OpenCL on this tutorial. It will take hours and hours. If you're interested, I can put some links down below. But yeah, the OpenCL version should be optimized. So what we're going to do for the second part of this tutorial is to dissect Tornado to see which optimizations are enabled and try to mimic those optimizations in our OpenCL C++ program. The end goal for us is to match the performance from the OpenCL C++ program to the TornadoVM level. Okay. Hopefully, this will give us an appreciation of what TornadoVM does under the hood. So before that, let's do a quick recap. Let me go back to this presentation and let's do a recap. What do we have here? So we have run the Java sequential implementation. This is a performance graph. Okay, the data used here was provided by JMH framework and the analysis of the 100 iterations in the OpenCL native code. So we can see the Java version, the sequential one, took around 2.1 seconds, 2 seconds. This is the variable of 1 second. The Java vector API, the parallel with the vector API, is around 155 times faster, which is quite impressive. And Tornado, in perspective, is more than 2,000 times faster. Compare this with the OpenCL C++ version. If we compare with Java, the OpenCL C++ is around 450 times faster. This means a gap between Tornado and OpenCL of 5.8 times faster. Right, so let's do the analysis now. What I'm gonna do is to go to our local repo. It will be simpler, not the TornadoVM examples, and let's compile the application. I don't think I have compiled this on this machine. Package. There we go. And let's run mxm. Let's run our program using TornadoVM only. There is an option I haven't documented, it's only TornadoVM, just to analyze. And we're gonna use this option from Tornado, it's called print kernel. And see, source set bars, we need environment, there we go. This option will spit the kernel that TornadoVM compiler generates. So let's focus on the kernel. This should be the equivalent of our manually written OpenCL kernel. We see that there are more things going on here. Let's try to dissect. This one loop here, okay, let's focus on the control flow structure here first. We see one for loop, second for loop, and another for loop. Kind of makes sense because our initial implementation in Java has 3 nested loops, okay, one for each dimension. And the final reduction is the innermost loop. And this loop, okay, iterates with the variable or for the induction variable I10. I10 is taken from I9. I9 is taken from get global ID 1. That's interesting because the first loop, in theory, as we put it in our C++ code, OpenCL C++ code, was get global ID with the 0 dimension. Let's take a look at the second loop. It says for this variable I13, using the I8 variable, I8 is declared here is get global ID 0. That's interesting because it seems like these two loops are interchange. In fact, this is a common optimization to increase performance, loop interchange. Let's take a look. So, this is our sequential implementation. Okay, we have 3 nested loops, and what the loop interchange does is to interchange any of these loops. In the TornadoVM case, it interchanges the 2 outermost loops. Okay, this is an important optimization to improve cache locality. And if the loops are perfectly nested, okay, without any statements in between, you can interchange any loop. For example, I and K, or J and K, or K and J, and so on and so forth. Not every interchange will give you the same performance, okay? And again, this is because the cache locality. So, in the case of TornadoVM, as I mentioned before, it interchanges these 2 outermost loops. If you want to know more about the loop interchange, it's a very good book that I highly recommend. It's called Optimizing Compilers for Modern Architectures. And the loop interchange is explained here in great detail. So, with that out of the way, let's run the loop interchange version in our OpenCL program, and let's see if we can match the performance of Tornado. Remember, Tornado is around 0.8 milliseconds, right? So there is an option in this program called -k, and we select the kernel. We're going to select MXM LI, which is the MXM implementation with loop interchange. Let's run it. And we see that the time, it used to be 4.7 milliseconds, now is 1 millisecond. That's impressive, just by doing this optimization. Let's take a look at the kernel though. So this kernel is this one, okay? And the only change was to interchange these 2 values over here, okay? Just by doing that, on the GPU with this size, you get quite close to 4 times faster, okay? It is quite good. So if we go back to our performance graph, we see that the loop interchange went from 450 times faster compared to Java to 1,900 times faster, but still is not faster than our TornadoVM version. So we need to dive deep into the optimization that TornadoVM applies. Let's continue with that. Let's go back to our code, the generated code for Tornado again. Okay, so I'm running this locally, not in the server, but locally. The kernel generated should be exactly the same. And apart from these 2 loops, we see that Tornado, let's go back to the innermost loop over here. This is the final, this is a reduction, okay? So it's taking a value from input matrix A, a value from input matrix B, and performing a multiplication. And so it's the multiplication and addition. But many GPUs and many CPUs as well has what is called fuse multiple add. Okay, it's FMA operation, fuse multiple add. In a single instruction can do a multiplication and an addition. Okay, and that's what it's doing over here. In fact, we can see that also from the TornadoVM compiler. To do that, I'm gonna open IGV. If you haven't used IGV, IGV is called Ideal Graph Visualizer. It's an amazing tool developed by the Graal compiler team to develop compilers and to debug compilation phases. So I'm not gonna explain how to install it. It's in the Graal repo, but essentially you launch it with MX IGV, and I'm gonna run it in background. And this is what you get. This is IGV. So now let's gonna run our application, okay, locally, because I have IGV locally, and Tornado has an option called --IGV. As simple as that. Let's run it only the Tornado version. We'll start with the Java just to compare results, and then at some point we'll connect with IGV. There we go. And if we go back to IGV, we see a bunch of information here. We see that it tried to compile, or compiled, the matrix multiply MXM TornadoVM version. If we opened, we see the OpenCL front end was used. And if we open again, we see a lot of compilation graphs. Each graph is before and after an optimization. For example, this is what Tornado starts with. Tornado, what we do is when you want to compile to OpenCL, you first call Graal to build the control flow graph. Okay, and this is the control flow graph of the Java method that represents the matrix multiply. I'm not gonna go in detail. So this is it's called sea of nodes, in which control flow and data flow are represented in the same graph. So I'm not gonna go in detail. This is quite heavy, but if you're in compiler development, this could be interested. Let me know. But let's jump directly to the FMA implementation, the FMA optimization. So FMA is applied in the low tier. Tornado has different tiers of compilation, which is called high tier with high level memory, so high level optimizations, mid tier with memory optimizations, and low tier with architectural specific optimizations. And if we see down here, we see FMA, OpenCL FMA, before and after. So we can take the diff by identifying exactly, hopefully you can see the pointer, what is the before optimization, and then we can see the diff by extending this cursor over here. And then if we scroll down, we see nodes from different colors, red and greens. What does it mean? Red nodes are nodes that are removed from this phase, and the green ones are inserted in this phase. So we see that the OCL FMA the optimization remove a multiplication followed by an addition, and inserted instead an OCL FMA optimization. This, from the compiler perspective, is a very, very easy optimization to do, and it's very powerful. Okay. So that was the optimization enabled at the compiler level, but let's see the effect that this optimization has. So if I go back to our program, or our C++ program, and run this application with the FMA kernel, we see that, well, it's 1.07 milliseconds, right? In perspective, if I put back the performance graph, okay, we see that it's actually a bit faster. Okay, but still it's not faster than Tornado. So we need to take a look at further optimizations that could apply for this kernel. So let's go back to our generated kernel by TornadoVM, and let's analyze again the generated code. So for the for loops, we see that the upper bound, okay, the bound of the loop is constant. It's a constant value. This potentially can trigger other type of optimizations like loop unrolling, for example. So the way it works is that once Tornado generates the OpenCL code, could be also the PTX code or SPV, it's the same because Tornado has multiple backends. Then it sends this code to the actual driver for final compilation. The driver has a JIT compiler. In the case of, for example, NVIDIA has the OpenCL JIT compiler that translates this OpenCL code down to the final binary for the GPU. In that process, because we have a constant value as a loop bound, it can trigger loop unroll. So let's try that. Let me show you how this was implemented in the OpenCL C++ code. So if I go to the kernel, the OpenCL kernel, that optimization is here. We see that in this case it's a loop unroll of 32. That was my first attempt to match the loop unroll factor equal to the number of threads per warp. Maybe, you know, it's an approach. So I'm not gonna go down into the discussion of GPU programming models, but NVIDIA GPUs, for example, they don't run a single thread, okay, ever. They run a minimum amount of what is called a warp group of threads. In the NVIDIA GPU, that means 32 threads. Other vendors might have different number. For example, on the AMD GPUs, the number is 64. It's called wavefront, and it's 64 threads that you run in parallel. So I try to match this number to the warp size, and let's see the performance. So let's go close here, it's clean, and let's run the next version, which is MXM Platform 2, which is the 4090, and the kernel is Unroll. And we see that it's actually a bit slower than we used to have, right? We went back in performance. Well, we might tune the loop unroller, maybe another number. We can tune it to 4, 8, etc. However, when I stay with 32, we might disable later on because I have the feeling that this optimization doesn't give us too much, right? But let's continue with this. So to discuss the effect of this optimization, we see that we went back in performance a little bit, right? When we compare with the Java version. So what other optimizations could be applied? Well, there's an optimization that, remember that Tornado sends this code to an underlying compiler, for example, the NVIDIA OpenCL JIT compiler. You can use it also to pass compiler flags. In the case of Tornado, it uses by default two flags. It's called CL math enable and CL fast relax math. What does it do? So CL math enable replaces the FMA optimization, the FMA instruction, with a math instruction. It's the same operation with reduced accuracy. The other flag, the fast math relax, what it does is that for valid data, okay, makes assumptions of valid data. For example, no nonce numbers, or not plus infinite or minus infinite, etc. It can lead you to faster compute at the cost of precision. There's a typo here. It's faster. Should be faster, not taster. Faster compute. Okay. You can take a look at all the flags available in the case of OpenCL by using this link. Let's see the effect of this optimization. And let's do unroll, and we pass -F to enable the same flags as Tornado does. And if we do that, well, it's the same performance as before. In fact, we haven't improved too much. If we put that in perspective with the whole compilation graph, performance graph, we see that it's actually a bit slower. And I have the feeling that the loop unrolling is affecting us here. So for now on, let's remove the loop unroll. Let's stay with FMA and the flags and the upcoming optimizations. So what's pending? Well, we have been focusing on compiler optimizations. However, there's another aspect which TornadoVM applies. I already mentioned at the very beginning, which is runtime optimizations. TornadoVM applies what is called a thread scheduling optimization. The thread scheduler is based on NVIDIA guidelines to schedule threads on the GPU. But why this is important? Well, in OpenCL, also in CUDA or SQL, etc., developers can select specific block of threads. Apart from the overall number of threads to launch on the GPU, let's say 1024 by 1024 threads, you can tune the block. So what's the impact of this block? Well, the block is important because if you want to share memory, sharing means sharing only in the same block. And the same block, threads in the same block can also synchronize. And this is an impact, selecting the size of this block has an impact on occupancy, okay? What is called GPU occupancy. What we want to maximize is the resource utilization and improve occupancy. There are many things in here, okay? So I'm oversimplifying things here, but so keep in mind that occupancy, so better occupancy doesn't always translate to higher performance. Usually yes, but it depends on the algorithm, it depends on the data accesses and so on. Right, so if the block is too small, we might underutilize GPU resources. If it's too big, we might, need to wait for a block of threads to finish in order to schedule a new one. Okay, so finding the balance is key here. Is key. Unfortunately, there is not a single solution. This is more like a try and error. Okay. As I say, NVIDIA has some guidelines to help you optimize this, and the TornadoVM runtime implements an heuristic using these guidelines. So let's see what Tornado does with the block. We can enable Tornado. Let's go back to our implementation. Over here, this is the, that's the one. And let's enable all of them with this flag, print, no, it's called thread info, -1 thread info. And let's run only Tornado. So it's called only TornadoVM. Oh, only TornadoVM. So what this will do is run a first sequential Java and then compare it with the parallel implementation. And every time we run, we see a debug entry. And this will tell us which GPU was used or which accelerator was used. In our case, it's the 4090. That's good. That's the one we want. And the block of threads used. So we see that the global work, so it's the total number of threads, was 1024 by 1024. That matches the dimensions of the input matrices. That's perfect. And the local work group size, this is the tuning, the thread, the block threads, is 16 by 16. That's interesting. So let's do that in our OpenCL C++ program. So let's remove the Unroll. Let's stay with the loop interchange and the FMA. And there is an option called -W. By the way, if you want to know all the options, you can see that with this script. So mmx -h. Okay, and you can see all the options. So what we want to do now is to enable the block of threads, a specific block, because we're assuming square matrices. The number we put here is n by n. So, okay, so let's do 16 by 16. So we're gonna enable again the FMA with the compilation flags with the group 16 by 16, and wow. We are now less than a millisecond. In fact, that number is quite close to the Tornado number. So let's see that in perspective in our performance plot. We see that when we run with the block 16 by 16, okay, we increase the performance and exactly matches what TornadoVM does. So we found it. Those are the optimizations that are enabled in TornadoVM. Okay, so we need to take out the loop and roll, by the way, because in this application it was not useful. But apart from that, all the optimizations were useful. In fact, to be more fair, as soon as you enable loop interchange with FMA and the right block of threads, you can match the performance of TornadoVM. Let's see the impact in relation of TornadoVM. So if we choose TornadoVM, as a baseline, let's see the impact of this. So now the baseline is 1. This means TornadoVM, and then the impact of the optimization. So the higher, the better. So the naive implementation is less than 20% of 25% of Tornado, and then as soon as we start optimizing, then we get exactly what Tornado does, which is quite good. Now, let's discuss more optimizations. If you know CUDA or OpenCL, and if you know the matrix multiply application, you might know that there are more to do than this. In fact, there are 2 key optimizations, apart from the ones I explained, that could be applied. One of them is the exploitation of shared memory, as in CUDA. CUDA calls it shared memory, and OpenCL calls it local memory. And it's basically moving data from the global memory to a specific type of memory that is faster to compute, to do the reduction. Unfortunately, TornadoVM, the upstream version, doesn't include this. However, there are some experiments of doing this in Tornado, achieving an extra performance of 2.5x, if I remember correctly, by using this strategy automatically. That was the purpose of this work. That was everything done automatically. Another important optimization that could be applied in this context is loop tiling. Okay, again, this paper applies some sort of loop tiling as well, giving us extra performance. However, these 2 are not upstream. With time, I wish these 2 comes upstream in Tornado. That could be awesome. So let's discuss the following. Is TornadoVM always better than native? Well, short answer, no. We just found an application which was better. That doesn't mean it's always better, okay? This application is not representative enough for all applications you can have with Tornado. Usually, the native code has been optimized, okay? That's a common case. However, this highlights, okay, the strength of Tornado. Unless the underlying code is optimized, then you can get some performance, okay? And again, the input application was written from the sequential Java, okay? It was not instructed to optimize the way it did, okay? That's something to keep in mind. So even though you might not get as good as performance as optimize OpenCL code or optimize CUDA, the thing is, Tornado, what it tries to do is to find balance between the programming effort and performance. We will discuss more numbers in a bit. Right, let's discuss something else. Since we have our program for matrix multiply, we can compute the floating point operations per second for each version and compare this with the theoretical maximum that we can get for each platform. So for Intel CPUs, Intel has a document. I'm going to put a link in the description down below about this document with the disclosure of the maximum theoretical performance in gigaflops for an amount of GPUs, right? I think it's one of the latest 4 generations, including this one, the one we're using, the i9-13900K. Following that document, the maximum performance, theoretical performance that we can get on that CPU is around 1.1 teraflop. Okay, so meaning 1,100 gigaflops. However, achieving the maximum performance is practically impossible. I will say that just reaching 60% is an extremely good number. Okay, it's very difficult. Now, if we compute the gigaflops that we obtain Hopefully that you saw that along all the executions that I did, right? So if we go back and I run all of them, you see that along with the compute time, so in nanoseconds and milliseconds, there is also a number, gigaflops per second. It's already compute for us, okay? So this in peak performance give us, for the Java sequential, 1 gigaflop. For the parallel stream, around 152 gigaflops. This in comparison with the maximum number that we can get is 0.09% and 13% of the total capacity, if you like. The Tornado case is a bit different because it doesn't run, in this case, on the CPU. It does run on the GPU. If we take the GPU spec, the NVIDIA vendor, NVIDIA, tell us that this GPU, the 4090, has the capacity of 82,000 gigaflops. This is 82 teraflops. This is massive performance. If we compute what we get around 2 teraflops with this application on Tornado. This is 2%, 2.5%, 2.6% of the total capacity. But if we look at these numbers alone, it seems like Tornado is performing purely, right? Okay, to understand this number, what we can do next is to take the native example from the CUDA suite and compare it with Tornado. So let's do that. By the way, we see here, I just ran in background, I was explaining the table. We see here that Tornado achieved around 2 teraflops, okay, for this application, which is quite good. Okay, let's go to the CUDA suite example. This is the suite from NVIDIA with CUDA examples. This is not OpenCL, this is CUDA. So the programming model is different. Well, the actual programming model is the same. The programming language is different. Right. And the compiler is different because this is the CUDA compiler, not the OpenCL compiler. But in this suite, there is also the matrix multiply. And we can run the matrix multiply on the same GPU with the same problem size. If we run it, we take the following. We take 6.5 teraflops of performance, right? Compared to TornadoVM, TornadoVM was able to achieve 2.1 teraflop. However, when we look closely at this application, it's called MXM, I think it's matrix multiply .CUDA. Let's enable the. There we go. This is the part in which the compute kernel is launched. Okay, this is the kernel launch, and we see that in between, so grabbing this kernel, we see an event for start and stop, meaning that the reported timer is just the GPU kernel. It's only the GPU kernel, not the total time, the end-to-end time. To be more fair, we can enable the profiling information in Tornado. Let's go back to that terminal. We can say --enable profiler console. And this will spit JSON entry, set of entry. Let's run only Tornado in this configuration. And we can see exactly the kernel time. And the kernel time is over here. So this is amount of nanoseconds executed. And there is a script here as well. I think it's called, in this directory, utils. Okay, it's a Python script. Minus time, the time in nanoseconds to compute. This is target to the matrix multiply with the square matrices, so keep that in mind. So if we do that, it says that it computes in 4.9 teraflops, okay, teraflops. In comparison now with the CUDA implementation, achieve 6.5 teraflops. 6.5 teraflops on that GPU means 7% of the peak performance that you can get on that GPU. Okay, so Tornado is performing quite well for this application in automatic manner. And this is not even optimizing until, using shared memory and local memory and so on. Right, so that's all I want to mention for today, and let's wrap up. By the way, This is the final performance report by JMH, okay, for each of the versions that we evaluate. All the Java versions on the top and the Tornado version over here. And those are the numbers that we took for the performance plots that we explain in this video.
So, this is the end of this video. Hopefully you learned something new. There is a lot of information in this video, so I will also put a link down below with a blog post that contains more details about some of the parts that I explained today. With that, I conclude and wait, today is Christmas Eve. I need to be more Christmassy. Let's fix that. Well, this is better. Merry Christmas, happy coding, and see you soon.